Okay, so once again, to get started, go to https://etk1.cct.lsu.edu. You can create your own account by typing in the code cookinglot0 at the bottom. Just follow the instructions. We found that this method of handing out logins by letting you create your own works much better than any other system for getting started. So I'll give you just a minute or two for everyone who wants to do this to follow along. We have a reasonably well-powered server here, so it should accommodate everybody in the room bashing on it. We'll see how well it works out. Sometimes it works extraordinarily well. Sometimes there are technical problems. All right, I'm going to get started. If you need to see this again, let me know. When you log in, you should see a bunch of different options on the left here. Not as many as I have because I developed the thing. But there's one called 111menu.ipynb. And that's the one you want to select. It's got a nice little image of the workshop at the top. And it's got a menu of notebooks culled for this year. We have our basic tutorial. We have a creating a new thorn with a heat equation tutorial. We have, and then we have some other notebooks that are going to be used by Lucas and Max later on today. We've got a Caparex Wave Toy, an Emit Cactus notebook, and some other things relating to an Emit Cactus down here. And they're going to go through that. There are some other notebooks down here. There's a second creating a new thorn one. There is using the cactus reduction interface. There's a Cellforce 1D code and visualizing output with WaveMol code. All of these should work, but we don't plan to officially use them. But if you want to poke around on your own during the workshop or say a week or so afterwards, you can play with those and they ought to work. And whether they work or not, you can pester me about them if you have questions. Any questions so far? All right. So how many people, and I want people online to raise their hands as well. How many people have never seen an Einstein Toolkit tutorial before? We have 2, 3 in this room. How many online do we have? Any? All right. So how many people would like to see information? I have 1. Okay, so I have 4. How many people would like to see a presentation, part of the presentation at least, on how to create a new thorn? Okay, so what I'm going to do is I'm going to sort of go light over the intro tutorial, and then I'm going to also try to go into the creating a new thorn, just so that people have more fun. All right. Okay, let's start. So start with the Cactus tutorial notebook, and it's got lots and lots of text about configuring and about how you could install on your own notebook, on your own computer rather. And the way okay, so in case you're not familiar with Jupyter Notebooks, Jupyter Notebook is a nice tool. It allows you to mix code and visualization and text and all sorts of things into one persistent storage format. It makes it easy to present and experiment and so on. These notebooks should all work if you just hit Shift-Enter all the way through. I mean, you might not understand anything that way, but it would work, and sometimes that's satisfying all by itself. But the idea is that you say, well, he showed me this. What if I change this parameter, or what if I change this thing? What happens then? Do I break everything? And maybe you do. But that's the point. Is you don't just have a presentation here. You have a lab that you can experiment with. And I'll point out some of the features of these notebooks as we move on. So most of them start with this magic setup code here, just to make sure that you have your paths and everything set up the way they need to be for the whole thing to work. And what we have is what we call an optimized build experience. So if you execute this cell, what it's going to do is it's going to unpack a completely built cactus. It's going to have all the .o files. It's going to have the .exe file. It's all going to be there so that when you type make, almost nothing will happen. If we had everybody in this room download just the source and try to build everything from source, that would be where we would stop, right? Because it would be just too much of a load. It would take too long. So we have this optimized build experience. But in principle, if you didn't unpack this, all the rest of the steps would still work. They would just take a lot longer. Okay, so how do you download the Einstein Toolkit? What we use is a tool called Get Components, which is a thing written in Perl because Perl was popular at one point in time. And it was the Python of its day, if you want to think of it that way. Okay, so it's sort of gotten long in the tooth. And what Get Components will do is it will download things called thorns. Could somebody get me like a small drink of some kind? And I just remember one of the lessons about giving talks that I always think I'm going to remember is that you should always have a drink, because you get partway through and you get a slight itch in your throat, and then, well, all right. I see. Okay. All right. Well, I'll somehow have to soldier on. Okay. So what we have these things called thorn lists. Thorn lists show how to. Oh, thank you so much. Thorn lists show you how to download code from multiple repos, and the idea is you can stitch together a code base from several different sources at once. This means that you can use part of the things developed at UIUC and part of the things at LSU, and they can all be go into one build, and you can work that way. Typically, you install into a directory called Cactus, and we normally use a tool called SimFactory to optimize our building and running of Cactus. You have to call setup silent on that to get it all, the way it's supposed to be. And then you're set up for building. So SimFactory build, in this case, I'm going to build on 4 cores, and I always give SimFactory a thorn list, and that's that, as I said, that list of all the software modules that we are going to use. And some of them are most of them are from the release, but we've made a couple of exceptions for special tutorials that we're giving. So you can just, this is not going to take too long, but it will take a minute or two. And that's basically how you build things. You have to build, you kind of need to build it that way the first time you build it, but after that, subsequently, if you just type make in the directory, it should just build. But we encourage the use of SimFactory for building, even though it's not strictly required. Okay, any questions so far?
Steve, I'm sorry, I'm fascinated in that cell. This is Bill. Fascinated in that cell that you have a slurm-n4.
Oh yeah, sorry. So one of the things that you can do with notebooks is you can have magics. These are things that start with % or %% that appear in the top of the cells. Some of them are built in, but I created one called slurm, and the notion is that if you put slurm -n4, what that's going to do is it's going to take the rest of the command that follows. It's going to throw it into a batch script. It's going to put it through srun and show you the output. So this way, when you do your build of Cactus, it will happen on our compute nodes rather than the head node, which hopefully should cut down on the load on the head node. Yeah, that's a magic that I created that got installed, well, into your environment when you ran this ET setup thing at the top, wherever that was. Good question. All right. So, am I done building? And then we have a hello world thorn. And all this thorn is going to do is all this. Then we have a hello world example. So what we do is we have active thorns and we have a thorn named hello world. This is a complete Cactus parameter file. We run it by saying create run hello world, and then we give it the par file name, and it should run. And I'm just going to pause for a moment there because waiting for this to catch up. Yeah, it should be just about done. So when you do things with SimFactory, we separate the creation of a simulation from its running. And so first you create the simulation, and then you can either choose to run it or submit it. If you submit it and you're on a system with a batch system, it will submit it to the batch system and hide the output. If you do create run, it'll run interactively. Create run sometimes doesn't work on some systems, some production systems, because of the way they're designed. Anyway, this code runs and it prints hello world like 10 times on the screen. And that indicates that you did it right. The next thing we have is running a star example, a TOV star. Now, I'm going to suggest that we don't run the TOV star unless you actually want to, and I could move to writing a new Thorn, because the TOV star takes about 20 minutes to run. I mean, you can just kick it off in the background if you like. But the TOV star is going to take a bunch of different thorns, right? So the idea is you have active thorns, and you name each thorn that you're using in the simulation, each software module that you're using in the simulation. And then some of these software modules have optional parameters. And as you can see, this thorn list for running a TOV star is quite complex. Frequently, when you and I could spend like half an hour just talking about this par file, but I'm going to try not to do that. I'm just going to say a few things about it. First of all, like most things of this nature, you usually get your par file by starting with someone else's and modifying it, and you work your way along that way. And we have several example par files in the toolkit that maybe you can start from, including gallery examples of black hole collisions and so on. All right. I'm not going to run this. I'll let you guys do it. But that shows you. So if you do, well, maybe I'll just kick it off anyway. I'll just run it with a really short time for me. So at the top of this file, we show the amount of time the code will run. And it's 400, right? So 400 in Cactus units. Cactus units are units where a solar mass is 1 and C is equal to G is equal to 1. And in case that's a little abstract for you, the time unit is roughly 5 microseconds. The distance unit is about 1.5 kilometers. And the mass unit is the mass of the sun, which is about 2 × 10⁻30 kilograms. So you can convert everything to something, all your simulations into something physical using those rough guidelines. So our time is 400. I'll just cut it down to 4 for me. That'll run almost instantly. Oh, let me just back up one more time. So at the top of this parameter file, there was another cell magic %% write file. So what that's going to do is it's going to take the contents of the rest of the cell. It's going to write it to the file named here. So all I'm doing here is I'm creating a file on the file system. So that means that this cell is functioning something like an editor, right? I can edit this cell and its contents, and I can just re-execute the cell, and it'll keep resaving that file for me. Questions? I know I'm going kind of fast, but I want to get to the creating a new Thorn part. Questions? Anybody?
Actually, just a comment. Sorry, Bill again. Feel chatty. The terminal is a good window in Jupyter. I think maybe most of us know that. So you can then look through the directory structure and look into these files, right?
Yes, if you
terminal.
feel, yes, so Bill is right. If you feel constrained by this view of things, right, there's a terminal option, and you can get to it a couple of different ways. You can hit on the plus sign here, and then you can go down to terminal and click on that, and it will open a regular bash terminal for you in case you're feeling lonely for a bash terminal. All right. So this is going to, so in this case, I broke up the create and submit steps of the TOV. I submit the TOV, It says the submit finished. It gives me a job ID. I can list simulations and it will show me, yes, that this is active and running. I can have this, this other command that says show output, and it will follow a running simulation until it's completed. And in this case, yeah, it's actually already done, I guess. Yep, there it is. It went, so you can see it went all 4 times, all 4 units of time. And then hopefully I left it, that's enough data for me to still plot things. So I can show list simulations, and that will show me all my finished simulations that are sitting in my simulations directory. I can stop a simulation if I want to. This cell is commented out because we didn't want to stop it, but it could be there. We have purge, which is kind of like an RM minus FR of the simulation. And we can have a get output dir, which is going to show you where the simulation data is kept. In this case, it's home Brandt simulations, TOVET, output 0000. The output 000, the output with 4 zeros is there in case I did checkpoint restarting. That 000 would increment with each checkpoint restart, and our various simulation tools would understand that all of those different things with those different numbers were part of the same simulation. We encourage people to plot with Quibit, which is a tool that's officially part of the Einstein Toolkit. It comes with some utility commands like plot time series and plot grid var. And if you run them on this simulation, I've got a whole bunch of stuff in chat. Am I missing stuff?
Yeah.
All right, good. It's all resolved. And so I can look at my row maximum, which in this case was only ran for 4, so it's kind of boring looking. And I can look at this, which looks a little better. This is my density profile. Now, by default, Quibit will resample data before it shows it to you, which you might find annoying, or it might be what you want, depending on a lot of things. And there are ways to make it not do that. And if you want to make it not do that, I have some code that you can follow along in here. Right, so this code, right, is going to look at the Quibit data in a bit more detail. So I'm going to actually get different parts of the simulation by reference level and then overplot them. So you can see what's happening here is we've got a coarse resolution, which is most of the grid. And then in this pinkish area, we have a more refined region, a factor of 2 refinement. So I won't go into detail about this Python code. Hopefully you can read it. And this shows you how to get the refinement level data out of Quibit and plot it. And then you can do calculations, right? You can calculate the cold pressure versus the pressure and plot them, and they pretty much are the same for this TOV star. And you can do full plots of the star. So the star is done in an octant, right? We use reflection symmetry to get the other octants because everything is spherically symmetric. And this is how much of the simulation I did. If you ran the full thing, it'll go out to here, and it will all line up pretty well. It won't line up exactly for a number of reasons. This is the central density plot, but it will all line up quite closely. Okay, and so that's just the very basic how to download, compile, and run the Einstein Toolkit with an example of a TOV star and the parameter file for a TOV star. And you can study that parameter file in detail if you like to, all right? Any questions on that? No questions, all right. So now let's take a look at how you write a thorn. Now this is in the process of changing as we move from carpet to carpet X. And this is based on the carpet version of thorns. but there's still a lot of this that's relevant. The stuff that isn't, the stuff that's going to change is how you write the loops. And maybe for getting started, you don't need to worry about that too much. So this notebook is going to start the same way the other one does, with the loading of ET setup. Yeah, the auto magic on. So you can type like CD // and even though that's not Python, the cell will understand that that command is intended to be a shell command and will actually change your directory. So that's what that does. There's a couple of little things of that nature. So it's just a little bit of niceness. That's what %AutoMagic does. All right. Okay, so this is going to define some variables. We want to have a home dir set up just to keep track of, just to use in different things. We're going to have a cactus directory, which is going to be a path join of our home dir and cactus. And then we're going to CD to the cactus dir. Now, in a lot of these cells, if you have something that's just in curly brackets with no $sign in front of them, it will understand that it's supposed to substitute a global variable from the current Python context into that space. It's kind of a little convenient way of pushing data back and forth between the shell commands and the Python environment. Okay, so to make a thorn, when in Cactus, we need to decide on a thorn name and an arrangement name. All thorns have to live in an arrangement, and all thorns have to have a unique name within your given thorn list. So in this case, I'm going to pick the name heat EQN and for my thorn name, and tests for my arrangement name. And I'm going to assign, in addition to just assigning that dictionary, I'm also going to assign the OS environment with those names. Just so I have those names, all set up. And that means if you want to write a different thorn, you want to change your heat equation to another thorn name and do everything all over, you can. And if you want to, if you just want to erase it all, you can do that also. Now what we're going to do is we need to have a certain basic structure to write a cactus thorn. And so we're going to set that up. And we have a little create dir command, which is going to print out that it's going to ensure that a directory exists. And then it's going to call os.makeDirs with exist OK true. That means it's not going to error out if the directory already exists. And we're going to create an arrangement directory. We're going to create a thorn directory. And we're going to create a source directory within the thorn directory, a test directory within the thorn directory, a par directory, and a doc directory. So we want to have all those things: heat, heat source, heat test, heat par, heat doc. And if we list our thorn dir contents, we're going to see these things, right? We're going to have a README and all this other stuff. That's what we've created so far. Well, actually, we haven't created that. I created that, I guess. You probably don't have all of this. You just have the directory names. Well, you're going to get this stuff eventually. I probably should have deleted it all. But the next thing you can do is you can create a README, and we'll do that with just the write file directive. And the Professor West made this version of the notebook for us. And so it's got his name, and you can spam his email address. And so if I do another list of the thorn dir, you should see your README there now. For those of you who need a reminder of the heat equations, we have them in equation form here. Basically, it's the partial derivative with respect to time is equal to alpha times Laplacian squared, right? We have, and then if you want to write it in finite difference form, it looks like this, where you have the time index on the top and the spatial index indices on the bottom. And the nice thing about the heat equation is you don't have to think about a time integrator, right? Now, Cactus has support for various time integrators, which you can use as plug and play through the Moll-Thorne, the method of Lines-Thorne. But for a heat equation, that's unnecessary. You can just use the Euler equation update and it'll just work because the heat equation is very stable. Okay. So there are certain basic files that have to exist in any Cactus Thorne. There's the interface CCL Thorne, and that's the first one we're going to create. And that's going to have, what that's going to do is it's going to define all the grid functions we're going to use in the simulation. So in this heat equation, we're going to declare a grid function named U, right? So there it is. It's in a group called the eval group, and it's named U. All right, so we're going to update that thing. You've already been told about ghost zones, but in case you don't remember, the idea is when we run these things in parallel, we can split the processors apart. So processor 1 can get, if we were doing a 1D array, right, you could get zones 0, 1 through 4, and the processor 2 could get 3 through 8. And the idea is processor 1 would be responsible for updating cells 0 through 3, but it's going to need to read 4. And likewise, processor 2 is responsible for updating 4 through 8, but it's going to need to read 3. So each of these two cells are what are called ghost cells. They're updated by the other processor, and on every time step we have to update them. We have to send a message from one processor to the other and update them. Are you with me? Who has a question? Nobody. It's because I explain things perfectly. And nobody is lost about anything I'm saying. Okay. All right. So the next thing we're going to make is a schedule CCL file. So Cactus has its own primitive sort of workflow engine built into it. And the workflow engine is basically initialize, call evolve a bunch of times, and call analyze and shut down. And in this case, that's the way this is going to work. So we're going to say the heat initialize is going to run at CCTK initial. Heat equation update is going to run at CCTK eval. And heat boundary is going to run in CCTK eval, excuse me, after heat equation update. So let's back up and look at this. Heat equation initialize is going to write the heat variable U, and it's going to write it everywhere. Okay. In the heat equation update is going to write the interior of U, and it's going to read U underscore P everywhere. What is U underscore P? U underscore P is the previous time level of underscore U. And let's back up just a minute and look at interface.ccl again. So when I declared the variable U in the interface CCL, I said that it had 2 time levels, right? Time levels equal 2. And those 2 time levels will be U and U underscore P. And if I wanted 3, then I would have U underscore P, and U underscore P underscore P, right? So those things would all exist. And so I'm going to use that in a minute when I write the code for these thorns. And then I have heat equation boundary, and that's going to write into the boundary. So, and when I say the boundary, what I'm talking about is the physical boundary. So if I go back up and I look at my 1D simplified code, the physical boundary is 0 and 8, right? There's an interprocessor boundary on 3 and 4, right? Those are technically ghost zones. These are boundary zones. And the infrastructure is responsible for keeping 3 and 4 up to date. And 0 and 8, well, whenever a synchronization happens, those are updated. And these are updated by our boundary routine.
1. How does processor one get the data before?
Before what?
For cell four.
Oh, so processor one, when it gets the data for cell four, it has to come from processor two. So that data has to be copied over. So that when this thing starts up, right, it writes data everywhere, right? The initial data routine writes data into all cells, not just the interior. And so on time step one, or time step zero rather, everything is just set up. Now, when I want to evolve things, right, I update my interior, and after I update my interior, then I synchronize. I copy zone 4 from processor 2 to zone 4 on processor 1, and I copy the data in zone 3 on processor 1 to the data in cell 3 on processor 2, right? Does that make sense? All right.
So Steve, before you go on, a couple of questions. Just to be pedantic, when this says writes, it's obviously not writing files, it's updating data structures, arrays, right? Correct.
I'm sorry. For some reason, I had trouble hearing you correctly.
Yeah, I may be cutting it out. It happens once in a while. So when we say writes, we're updating data structures, not obviously writing files.
What I'm talking about is updating, not files. I'm updating grid arrays in memory.
Right, right. And have we specified yet how many ghost zones in any of
We
these
have
cells
not.
yet?
We have
Okay.
not specified that. At no point in this have we specified that. That's going to go in the par file. We're going to specify the number of ghost zones we have in the par file. And if we get that wrong, we can shoot ourselves in the foot.
Okay. Thanks.
But for the heat equation, we're going to have one ghost zone. You could rewrite the heat equation to use a higher order derivative and get more ghost zones if you wanted to do that. But that's not the way the notebook is set up by default. Okay, so we've got the schedule file. Next thing we want to write is the parameter file. And I think in this case, our parameter file, oh, it does actually have something. It has this thermal diffusivity term. That's the official term in case you don't remember that from your basic physics class.
Question about the schedule.
Yes.
Are the only choices for where you schedule things are CCTK initial and CCTK evolved?
No, there's a bunch of different choices, and your various thorns can create more choices. So in your schedule CCL, you can, instead of scheduling a function like we're doing here, you can say schedule group, and that will create a new schedule group, and you can insert it into the schedule tree. And you can use these before and after things to tell it where to go. Oh, I'm sorry. The question is, are these the only places you can schedule things? And they aren't. And so you can create other groups and insert them into the tree at these bins. But in addition, when Cactus starts up, if you want to go back to your tutorial notebook, if I want to go up to where I ran the simulation, all right, so if I go up to this output from my simulation and I go to the top, you'll see when it starts up, it says the Cactus code 4.18, and it's got a cactus drawn with ones and zeros and some other stuff. And it's activating all the different thorns it's using. And then it shows you the schedule tree that it's currently using. So it says, this is the CCTK startup bin. These are all the functions that are running in that bin and the order they're running in. There is a group called HWLock startup, and it contains, HWLock version. Then there's CCTK ROG. Then there's a group called MOL register. And you can just sort of, this whole big long thing is a diagnostic that shows you the schedule trees in all the different places you could potentially schedule something. And that's, this is really an obnoxious amount of text, but it's occasionally very useful if you want to figure out what your code is doing, or if you are looking for the correct place to schedule something. But the simplest things to tell you for the purpose of a heat equation, are initial and evol. Okay, any other questions? Yes.
For time solution, do you just have like 5 time levels?
Yeah, so if you go back and look at this one and you scroll up, this is our parameter file, and I'm looking for, oh yeah, okay, so the question is if I'm running RK4, if I'm running Runge-Kutta 4, which I'm not set up to do with the heat equation at all, do I need to have like 5 time levels was the question. And the answer is you need 4 intermediate steps and a scratch level. The method of Lines-Thorne is the thing that allows you to specify a time integrator. And instead of specifying your Thorne to run in CCTK evol, you would run in one of the mol calc RHS bins or something like that. And you would also you would tell mol that you wanted to use RK4, and then you would give it these other 2 parameters. It would be nice if it figured these 2 parameters out by itself, but for some reason it doesn't. Okay, cool. So if you want to use RK4, you would copy these lines out of this file. All right. And the parameter file. Now, the parameter file is mostly comments in this case because we only have this one parameter. But we're going to show you the other kinds of parameters you can have. You can have strings, you can have true, false. You know, you can have integers, you can have floating point. And you can do calculations in here. The parameter file parser understands basic math and order of operations and so on. Okay, and then we have something called configure. And configure, almost any Thorne that you're likely to write, configure.ccl will be empty. Maybe that will change if once we get to Carpet X, and then it'll always have like the same things in it. But in any event, one of the things that goes here is if you had a Thorne that explicitly needed to interact with MPI for some reason, which hopefully you don't need to do. But if you did need to do it, right, then you would put requires MPI, and that would make sure that when these source files are compiled, you've got the right headers for MPI. And likewise for HDF5, if you need to explicitly interact with the HDF5 lib and you need those headers, this would make sure you got them. But most of the time you can leave that blank. Okay, so that's all the boilerplate, right? Now we can write actual code. And the code, of course, will also contain boilerplate. So some of the standard boilerplate are these 3 header files here: cctk.h, cctkarguments.h, cctkparameters.h. And the way you write a Thorne is you have a void, you have your Thorne name, and then you have cctk arguments, and that's a macro. And what that's typically going to expand to is it's going to expand to the pointer to a CGH data structure, a pointer to a CGH data structure, and the name of that variable will be cctkgh. And that gets used in a bunch of places during your loops. You declare cctk arguments heat equation initialize. So what that's going to do is back when I wrote the schedule for this Thorne, for this initialized Thorne, I don't know if you remember this, but what I said is it writes you, right? And it writes you everywhere. Okay, that information gets used to construct declarations in here so that I can just access u, the variable u, and I can assign values to it. It will declare a valid reference to that variable for me. And anything I put in my read and write directives will get declared here. And this is part of a correctness check, right? I said I read and wrote these things. If I try to read and write other things that aren't in that list, then they won't be available to me, right? If I said I was going to read something and then I try to write to it, I'll get a compile error because it will be declared in this function as a const, right? So there's a part of a correctness check that we're doing the reads and writes in the way that we said we would do them. All right, so another thing that CCTK arguments does, declare CCTK arguments does for you, it declares some magic variables that you can use to write your loops. CCTK underscore LSH 0, 1, and 2, it's an array of 3 integers, allows you to write a 3-dimensional loop. So this is the upper bound. CCTK LSH 0 is the upper bound for the x direction. LSH 1 is the upper bound for the y direction, and 2 is for the z direction. We can, now internally, Cactus is not using proper 3-dimensional arrays. It's using a giant 1-dimensional array. And what you do is you use this function called CCTK GF index 3D. You pass it CCTK GH and then IJK, and it figures out the right position in that big linear array and gives it back to you as a size t, which in here I'm storing as IJK. And now I can access, I can say exponential of the x variable, the y variable, the z variable, all in that way. Let me scroll back up here a minute. Just want to check something. Yes, go ahead, ask. Back when Cactus was written in 1997. And one of the novel and forward-thinking things that we wanted to do at the time was we wanted to be able to interface languages arbitrarily. In particular, we were thinking of Fortran and C, because those were the languages. And there was no ANSI specification for how you communicated between those two things at the time. And they tended to do things in reverse order, right? So we wanted to create a fairly uniform interface between C and Fortran, and so that was the way it was done. The other thing I didn't mention, this says it reads grid coordinates everywhere. So that's the X, Y, and Z that you saw. All right, that's going to give me that. Okay, so what I'm able to do then with this initial data routine is I'm going to initialize my heat equation problem domain with a big Gaussian pulse in the middle. And of course, what's going to happen is that heat in the middle is just going to diffuse outward until I get something flat, right? That's what heat equation does. All right, the next equation is evolve. Okay, and what evolve is going to do, it's going to do that update that we saw. And so in order for that to work, I have to get the stencil offsets for all 3 dimensions in my heat equation. So I have ijk, I have I plus 1 jk, I minus 1 jk, ij plus 1, ij minus 1, ijk plus 1, ijk minus 1, right? So I get all the points in each of the orthogonal directions. And then I can create my Laplacian, right, by taking this formula from all the preceding, from all those different points, right? And I've named them such that I can map them on. So IP1 JK is I plus 1 JK. And then I can construct my stencil that way. And then I say my U at IJK is equal to my U previous at IJK plus DT times alpha times the Laplacian of U, right? And that's my heat equation. And hopefully you can all see how that maps from the equation to the code. And I didn't execute those cells. I meant to execute those cells. Okay, so I've gotten my init cell, I've got my evolve cell. I'm going to write my boundary cell. It's going to have that same boilerplate that everything has, those same 3 header files. It's going to have arguments and parameters. And now I'm going to have, by the way, if you want to know the number of ghost zones that you have, you can get them from these magic variables too. CCTK underscore n ghost zones is the number of ghost zones in the z direction. Y is G1, 1 is in the y direction, and 0 is in the 0 direction. And I guess I used them up here too. I just forgot to talk about them. So here's the number of ghost zones, and I'm starting, from KZ, and K goes to the CCT LSH minus GZ. So I'm iterating over that interior, right? Okay. But on the boundary, I want to just go over the exterior, as it were. And so I have to write this 6 different times because I'm on a cube and there's 6 different faces. And even though I'm just going to write 0 every time in every one of these places, this shows you basically how it can be done. So there is a variable called CCTK bbox, and that will take on, and 0 will be the lower x boundary, 1 will be the upper x boundary, 2 will be the lower y boundary, 3 will be the upper y boundary, 4 will be the lower z, and 5 the upper z. And in each case, right, I'm going to fill in that face of the cube on the boundary with 0. So let's save that. Yes?
So you set a Gaussian everywhere,
Mm-hmm.
including the boundaries.
Mm-hmm.
But then at the next step, it will just turn it to 0 at the boundary.
So the question is, I set up the initial data everywhere, and then on the next step, I am turning it to 0. And you are pointing out that this is inconsistent. And yes, you're right, it is, but it's very close to 0. I mean, I suppose what I really ought to have done here is figure out that same exponential and written it in there, and that would be more correct. On the other hand, I could be saying, you could think of it this way. What I'm doing is I'm putting that Gaussian pulse into a heat bath with walls that are held at 0. And so eventually it should all just go to 0. So yes, you're right that there is a slight inconsistency there. I set something initially and then I changed it. And probably I should do something more consistent. Like maybe I should set those boundaries on the initial one in that same way or whatever. But if I'm looking to find out what happens if I have my walls held at 0, then this is a fine thing to do. All right. So now what I'm going to do is you need to have a makefile, right? A sort of a primitive makefile for your Thorn. And those are pretty easy to write. So they go in the source store. It's called make.code.defen. And inside here you have a variable called sources. And basically you just take all the files you want compiled and you put them in that list. And whether it's C or C++ or Fortran, it will pick the right compiler and link it all together. Bless you. So let's create our make code defen. All right, and all right, cd to cactus stir. Everybody with me? Okay, so here what we're going to do is we're going to get our thorn list. There's a file called thorn list that gets created when you build something. And what that is going to do is it's going to be a copy of whatever you've passed to the -- thorn list when you ran SimFactory. And what I'm going to do is I'm going to take this new thorn called tests heat equation, and I'm going to write that onto the end of my thorn list, and then I'm going to show a tail of that file. So I write this cell out. What I'm doing is I'm putting tests heat equation at the end of my thorn list inside that configs directory. And the notion is once that's there and I tell Cactus to build, it's going to start building my new thorn. If I don't put that there, Cactus will just ignore it and say, oh, I know you don't want to build that. I'll leave it alone. All right, and so now I'm gonna build this, and this one I probably should have updated this one to use my slurm command, but I don't think it really matters. I think this will be quick enough. Oops. Now, a lot of the boilerplate that we've walked you through here, I mean, you need to have it all, and you need to think about what goes into each of these CCL files, these Cactus code language files. You can create them sort of semi-automatically if you type at the command line, make Newthorn, right? It will give you some prompts, and it will make the directory structure and some of the files for you to help you get started. But for the notebook, you can't really do that in the notebook because it doesn't let you interact in the same way. And we want to show you all the different pieces in detail anyway, so we just sort of redid that here. But there is a make Newthorn that you can use that will ease the writing of the boilerplate. Okay, and so that's compiled. And now I'm going to make a par file that runs this heat equation and put it in my par directory, call it heatequation.par. Let's see, full of warnings, highlight warning messages, terminate based on time, final time is 5, active thorns, carpet, carpet lib, carpet interp, carpet reduce, carpet slab. You know, you have to go deep into the details to understand why each of these pieces is necessary, but you can just, you know, copy, as I say, you copy pieces of other parameter files typically. I put these, turned off the verbose options. And all right. Yes.
So Steve, Steve, I see that the final time at the top, I don't see a delta time yet. Am I just missing it?
There isn't a delta time there. There is only a final time. So it's
Okay.
we haven't shown how it figures that out, but basically it's going to base it on the Courant factor based on the spatial resolution. Okay. I think I might have a time thorn in here. I have to look. Does that answer you, Bill? Bill?
Yes, yes, it does. Sorry, you're not
Okay.
seeing me. I'm sitting here thumbs up and silent.
Oh, okay. Yeah, no, I am not seeing you. I am not seeing you. Yes. The default time, well, time units are 5 microseconds, right? The Cactus time units, it's assumed that you're doing that. For the heat equation, that doesn't really make any sense, of course, but so the time units are going to be consistent with whatever other units you've chosen for things. So if you just, yeah, so that's right. So normally Cactus time units are by default, if you have something that needs to make an assumption about time units, it's going to assume solar mass G equal 1, C equal 1. But if I'm doing a heat equation like that, there's nothing that I'm using that's really relying on that assumption. So I can just understand it to be whatever I want it to be, right? It could just be MKL units if I want. Trying to see. So there's a NAND checker. So one of the things that you can do is this is a correctness checking tool. Whenever data is uninitialized, the framework can put a NAND there. And so if you see NANDs in your data, the tool can automatically stop your simulation once it sees NANDs, and you can debug why there are NANDs there. Now, this can be an important thing in correctness checking. Here we're specifying our grid, and so we're using the coord base, and we're using the spacing method. So we specify x min, y min, z min, x max, y max, z max. We have number of cells in each of those directions as 40. We specify our boundary size. Our boundary size is here. Hold on. My computer is claiming it's thirsty. All right. Okay, so I include the time thorn, and then I have a DTFAC of 0.0125. So that was in reference to Bill's question about the time step size. So what it's going to do is it's going to compute my Courant factor based on my spatial resolution, and then it's going to multiply it by 0.012 or 0.125 or 125 rather. And so that's how that's going to work. Okay? So that thorn time provides you access to DTFAC. All right, I put active thorns. I have to put my new thorn here, otherwise it won't be available to run. IO output dir, we always put par file there. That just means that I want to create an output directory that has the same name as my parameter file. Then for output, I have various output routine. We have various output routines. We're going to put in out2d every 16 steps. We're going to output the XY direction, not the ZY or not the YZ or the XZ directions, because we're just not going to visualize those, and we save time that way. We're going to write out in 2D variables. We're going to write out the heat equation U, but we're also going to write out the grid coordinates, but only once. And so that's our par file. And then we can run our simulation. Let's see, that's our simulations directory. We're going to remove, I'm going to remove a previous simulation with the name heat equation, just so because SimFactory by default won't let you rerun a simulation by the same name. It's trying to protect you from overwriting something that you might want to keep. But most of the time for me, I'm doing tutorials or just debugging, and I really do want to get rid of it. So, all right, and then I'm going to run the thing, and it will run very quickly. It's only going a short time, and it collapses basically to nothing almost instantly. And then I can go through visualizing the output, which I've got a bunch of HDF5 files. And in this case, I'm using, I think I first walk you through using NumPy and H5Py in sort of a raw fashion to pull out the data. And then you can plot the surface. And yeah, it looks like that. And I can do an animation. Getting animations to work properly in Python with these notebooks is surprisingly finicky, but these notebooks work. So if I start, you can see the heat just dissipates nicely, as you might hope. And I did not do a Quibit with this one. I guess I didn't do a Quibit. Let me just make sure. No, I did do it with Quibit. I just put it after that part. Okay, so I'm going to do the same thing again, but this time we're going to use the Quibit interface, which is our officially supported thing, and we'll plot the same thing, hopefully in a more intuitive way. All right. And that takes you through that all up to the basics of writing a heat equation. For those of you who are following along, are your brains overloaded? Or do you have more space in them? You have a tiny bit more space. Yes. They can mean whatever you want them to mean, but they will be logically Cartesian, right? So what? Oh, yeah. So the question is, do the X, Y, and Z have to mean X, Y, and Z? And so they have to be logically Cartesian. You can interpret them any way you want. That could be, your X could be a radius and your Y could be an azimuthal coordinate if you want, but you have to make sure yourself that all of the rest of your equations follow through with that understanding. Any other questions on that? Now I have until 5, right?
So back to the boundary thing, I changed the size. I made this grid really tiny.
Okay.
And I got nans. I made 1 minus 1 minus 1.
Yeah, okay, it makes sense. You got nans. Congratulations. So what he was saying was he made the box really tiny. He made it ones, and then he got nans everywhere, and that's good, I think. Um, but it's just we laugh, but it's good to do these experiments, right? This is the reason why you have notebooks, and you're not going to figure anything out if you just accept everything. I have this course that I teach in parallel programming, and I still haven't decided whether this is a bonus or a plus or a minus for the course, but the book we use, almost every coding example in the book is wrong. It's really quite remarkable how wrong it is. I mean, some of the bugs are really obvious. They're like syntax errors and things. And code, and there's just code that just doesn't do anything, that if you changed a little would do the right thing. And then there are other bits of code where the bugs are really subtle and you could spend, hours figuring out why it doesn't work. Or even figuring out ways to show that it isn't doing what it thinks it's doing. But it's, and I read somewhere, there's a study they were teaching, somebody was teaching a class and they taught it two ways. One with perfect slides and one with slides that had a bunch of errors in it. And the ones with the errors, the kids learned more because they weren't just trusting what they were saying, and they were paying attention and looking for things that were wrong, which meant they had to understand it well enough to know if something was wrong. Okay, so it's good to have mistakes. That's the bottom line. The art of multiprocessor programming. But I think every time I've gone in there to find a bug, to look at any piece of code, I found a bug. And, okay, this is a digression, but there's, I can show you one of the bugs. Well, maybe I better not. That's too much of a dig. So one of my favorite ones is the bug in their merge sort. And it really threw me because one of the things you need for the merge sort is you have to calculate the midpoint of the array. And they said mid equals parentheses high minus low, close parentheses over 2. And it's plus, right? It's not minus. And I actually coded the thing and ran it before I realized that it didn't work. Because somehow or other it looks right. Midpoint is high minus low over 2. Of course it isn't, but somehow it looks right. Anyway. And I bet you if I just showed you that code, you wouldn't see anything wrong with it. Yes?
It might be, what exactly is the scope of the form? I'm getting that it's some sort of.
Yeah, a thorn is a module, right? It is a if you want to think of it, it's a module for this type of thing. So the notion is that and the concept of the Cactus Toolkit was that we wanted to divorce as much as we could physics from computer science. And so we have thorns that do infrastructure. For example, you've got I/O thorns, which do nothing but write to the disk, right? And you figure out how to optimize that. And you can say, because you've got this thorn written this way, my I/O thorn writes these variables, it writes them this often, right? When the person goes to write their physics code, like me, when I go to write this heat equation, I don't have to think about I/O. I don't have to think about how I save it to the disk or how I want to visualize it later, right? And that is an enormous relief from the science programmer. I recently, last couple of years ago, I compared a simulation of Cactus to another code, and Cactus was like 10 times faster than the other code because of the I/O, right? The other code was doing I/O in a very slow way. And I/O is one of those awful things where your simulation is useless if you don't do it, but it's also one of the things that can totally kill your performance. So you ideally you want somebody else to do it for you if you can. All right. Where were we? So I've got some more time. I could just show you briefly the wave equation notebook. which is slightly different from the heat equation notebook. The major difference is that it uses the Malthorn, that instead of scheduling in calc, instead of scheduling in eval, it schedules in mal calc RHS, right? And there's a bit of a tricky thing that you need to notice there. And given that I have half an hour and you have this much more room in your brains, and I'm holding my fingers an inch apart, that might work. So if we want to go back to the menu, and you scroll down to previous notebooks from previous years, there's creating a new Thorne wave equation. Okay, and this one is almost just like the heat equation, right? I'm going to do almost everything the same way. I'm going to look for things that are different as I'm just executing cells, right? I'm just looking for things that are different. The README is pretty much the same. Obviously, the text for the math is different, but it's similar. When I go to declare my my grid functions, I'm going to have a URHS, a KRHS, and a U and a K. So I'm splitting my wave equation into two variables the way one normally does. And you know, the sort of the position and the momentum, if you think of it as a string or whatever. And then the right-hand side is going to be the time derivative. So when we did the heat equation, we looked at U and U previous. But most of the time, when you write Thornes, you're not going to do that because you don't have the utter stability of the heat equation and the lack of need for mol, right? So what we're going to do here is we're going to tell mol, these are the variables that I'm evolving, and this is the time derivative of those variables, according to me. And given that information, mol, you figure out how to take a time step for me. Okay, that's what's going to go on here. And so I'm going to write the schedule as I would before, pretty much, except I'm going to have something called wave equation mol register that runs in a time bin called mol register. And I'm going to have my RHS equation, the thing that I did for an update before, I'm going to put that in mol calc RHS. And then I have my boundary routine as before also. Another thing I forgot to point out, there are these storage declarations. You need to declare the storage for your different variables here. Otherwise, Cactus won't allocate storage for them. The idea is that at least when Cactus was originally being developed, we were very memory constrained on most computers. And you had to turn off as many variables as you could just to fit in memory. This tends not to be true anymore. But anyway, so you need to specify that there. Okay, so parameter files, I have no parameters. Configuration, there's nothing to configure. Okay, so let's take a look at mol register. This is a new thing. So in order for mol to do its thing, right, it needs to know what variables I'm evolving and what right-hand sides correspond to those variables. And so I have to tell it explicitly. I'm going to say that the eval group and the RHS group are, I'm going to get the group index for eval group and RHS group, and I'm going to hand them to mol register as group and RHS. And this tells me that these things correspond. That tells mol that, let's go back up to interface. That tells mol that U corresponds to U underscore HS and K corresponds to K RHS. The same order they're declared. They line up, right? Okay, so now that mol understands that, it can construct any time integrator we want based on that information. And right, so I did the register, and that tells mol, hey, those two things are connected. And then I have my init routine, which looks much like the init routine before. I'm even using an exponential, right? And I have my evolve routine, and my evolve routine, again, looks very similar, right? I have my Laplacian as before with the dx squared and the dy squared and the dz squared, which come from these special variables, CCTK delta space, right? And I get my time variable from C to K delta time. And everything about this is very similar to the heat equation. The looping is done in the same way and so on. My boundary routine, it's pretty much a copy of it, except I'm saying my right-hand side for U is K, my right-hand side for K is 0. So that's going to produce a standing wave. And then my make code definition, I'm going to have init, evolve, boundary, and mol register. Okay. And now, with that little bit of change, right, I now have the ability to make use of mol. And in this case, I can say I want the run cut of 4. I'm going to have the 4 intermediate steps and the number of scratch levels there. And I can compile and run all this stuff the same way I did before. Oh, here's another thing that's new. We made a utility. So the Einstein Toolkit has gotten quite big, right? I don't know how many of you have tried to check out and build it from scratch, but there's like 1,000,000,004 different thorns in there now. And you might not need all 1,000,000,004 of them. And so we have this thing called make thorn list. And what it's able to do is it's able to read a list of parameter files and say, these are the thorns you need to build a code that will run that simulation. And then you can build just those thorns. So this creates a new thorn list for us. It's in Cactus. Inside Cactus, there's utilities, scripts, and then make thorn list. It's just part of the standard install.
Does it take the thorns from your master file, or is it also able to add any thorns that might, where there may be dependencies, even if that's not scheduled in your master file?
Okay, so the question is whether it's able to figure out whether, what thorns is needed, even if they're not in the parameter file. So the idea is you have to give it a master thorn list, first of all. So the master thorn list is going to tell it what things you have installed. So that's what's available to it. But when it looks through the parameter files, it's going to have a knowledge of what thorns you need. And if one thorn needs another thorn, it knows about that. It's going to go into the directory and it's going to see the dependencies and it's going to trace those out. And many thorns have optional dependencies. And if those are installed, it's going to grab those. So it's pretty smart. I won't say it's infallible. And it's probably always going to throw formalin on there, and you never need formalin. But anyway, formalin is one of those things. It's very useful if you're actually doing science and not just doing demos, right? So what formalin is going to do is it's going to capture all the data from your build, all the source changes. Maybe you made a bunch of little tweaks to the source file somewhere and you forgot you did it, right? This is going to make sure that you've got all that. I remember when I was working, in the relativity group at UIUC, long before there was a Cactus, and we had this gravitational wave simulation, and it appeared on the cover of Science. And 2 years later, nobody knew how we made it. I mean, maybe we knew the name of the visualization tool, but no idea what code produced it. Okay.
So Steve, do I remember formalin puts all that information in the executable or somewhere?
I'm sorry.
Yeah, sorry.
I'm sorry. Go ahead.
I was just asking if it hides it in the executable, which is what I thought happened.
So formalin is going to put the code into the executable somehow. It's going to save all the source code for you in human readable form. I'm not sure the details of how to get it out or anything because I've never done that. Ah, okay. So if you heard that, Peter said it's extracted automatically whenever you run the code into your output directory. So,
Okay, thanks.
all right. So anyway, oh, I have a broken something. Test missing CCL file. What am I missing? I must have forgotten to click shift on something. It says missing CCL file, but it doesn't tell me which one. Look at that. Missing CCL file. That's unhelpful, isn't it? All right. So I'm just gonna. Oh, that looks like the one I missed. I missed schedule. I missed schedule. That was the one. Okay, so now if I go down here, obviously it doesn't work if you don't hit all of them. Yeah. What did he say?
You can now run anymore. We provide a Python code for GDB to extract it from the executable.
Okay. All right. So that's good. All right. And then here is my run. Good. That all worked. And oh no, wait. Okay, so it's going to run from here, and then I can go on to visualization. Okay, it shows you the files there that it wrote out. I think, and this is following the same recipes for visualization that we used in the heat equation notebook. And it shows you a pulse there. And this should be an animation when it finishes, which should be any minute. There we go. Look at that.
I feel like we should have handled the boundaries a little differently.
Well, I was doing the, I mean, you can do the boundaries differently, but I was doing something, you know, that's just reflecting. And maybe that isn't what you want. Maybe you don't want to have waves in a box.
It's pretty.
But I think it's kind of pretty in its way.
The initial pulse, when it falls down, it picks up like red. Is that like a numerical error?
No, I think what's happening is it starts up all above zero, and then as after it passes, it goes below zero.
Why wouldn't it just go?
Well, it's a wave, right? It's going to be traveling plus and minus, and it's superposed on the front there, and it's going to turn more into a sinusoidal thing as it propagates out. I mean, it's what the wave equation does. I'm not sure how to explain it. Why does it drop down? I mean, it's kind of like. So picture, how about this? Okay, why does it drop down? So picture you have a guitar string, right? And you've somehow plucked a guitar string so it's up like this, pointing, right? When you let go of it, it's going to go down. It's not going to just settle like this and bounce up and stay level. It's going to go back and forth, right? That's what the wave equation does. So it's kind of like that. It's kind of like I've plucked the surface of a drum. When it comes down, it's going to go past zero. That's just with the wave equation, how it's going to respond. It's kind of like standing wave. It's all reflecting, and I think if I chose them correctly, then you could imagine. So if you have a zero, right? If you have a wave equation, right, and you have zero, you can sort of think of it as a combination of a wave coming in and just exactly canceling, right? and that will keep it 0 at the boundary. And so that's kind of what happens there. That's how it works. Anyway, so the nice thing about the wave equation is you have to actually use mol, and that means you have to have mol register, and that's sort of an important piece of probably any real physics simulation you're likely to do. The heat equation is just, it's easier because you don't have to do that, but it's really not that much harder to handle that last piece. And that is your special on-the-fly whirlwind extra content intro to the cactus tutorial framework. Any final questions? Okay, so the tutorial server is going to remain up probably even after the workshop for some amount of time. I can't guarantee you how much, but it should be there. So I will be here, you know, tip your waitresses, ask questions if you have, if you have any, you know. All right. All right. And I guess you can all go home now.
Thanks, Steve.
Yep.
So I guess I will ask this if you're still standing there. So if you do adaptive mesh refinement, then you're going to have to look through a whole nother set of CCTK functions probably,
Well,
right?
okay, so adaptive mesh refinement, in principle, if you wanted to take the wave equation code that we just did and put adaptive mesh refinement, what you could do is you could go to that TOV star example and you could copy the relevant parameters out of there, right? The idea is you could just create, you could say, I want to refine around this box with this radius, and the carpet framework should just do it, right? You should be able to get adaptive mesh refinement in your wave equation without changing your code at all, just the parameter file.
Okay.
Hey, Bill.
Hey, Steve, and everybody else, most of whom I don't know.
All right. Oh, yes, you can have the microphone. And this.
I guess I could do that. Yeah, so that's the end of the day, and we will see each other at 9 tomorrow for more exciting talks. You know, and on like a street.